On the midterm.
Okay, here we go. So, real quick, before we jump into this stuff, we left off yesterday. I felt like we just got a little bit pinched for time on this last problem. We were solving a trig equation, right? The calculus was easy. We were trying to find where f of x has a horizontal tangent, so we set the derivative equal to 0. We took the derivative and set it equal to 0, and we ended up getting this trig equation, meaning an equation involving a trig function, right? And then we were solving the trig function. I think you were pretty good on this, right? We isolate the trig function, and we get the answer cosine x equals -1/2. And then being as there's no restriction on the domain here. Now, sometimes problems like this will say find all solutions on the interval from 0 to 2 pi or something like that, right? And so then you're only going to get a finite number of solutions, but it doesn't say that. And so it's asking the question, what are all the infinite places on the unit circle? Or we'll look at, when we're done with this, well, let me forget, I'll show you what this looks like. Let's just make sure we also look at a representation in terms of like what the sine function, or what this function looks like too, okay? So we want to actually graph it on Desmos and see that the two things correspond, because it's useful to kind of pull those together. But let's focus on the unit circle first, because that's where we do our work in trig most of the time. So where on the unit circle is cosine equal to -1/2? Well, any point on the unit circle, remember, and you told me this yesterday, you confirmed this yesterday, any point on the unit circle, here we go, always has coordinates where it's at angle x, right? So we'll say that this angle right here is x, has coordinates cosine x, sine x, right? So when we say cosine x equals -1/2, we're just looking for all the places where the x coordinate is -1/2, and there's 2 points on the unit circle where that happens. It's going to happen at all the multiples, or all the laps, all the circuits of the unit circle where we end up at 2/3 pi, right? Which means we have to do 2/3 pi plus k times 2 pi, or usually we'd say 2k pi or 2n pi or something like that, where k just represents the set of all integers, right? Does that make sense?
Yeah.
Okay. We got another one here at 4/3 pi, so we have to do the same thing, right? We get 4/3 pi plus 2k pi. Okay. Now, what about the second one here? The second one, I want to look at this real quickly. The second one, they want to know where it has a slope of 7. So we already took the derivative. There's the derivative function. We're going to set it equal to 7. Okay, so we're doing for part 2. There's our derivative. Want to know where it equals 7. I subtract 7 from both sides, and I get the result 14 cosine x equals 0, and that's true when cosine x equals 0, right? So where on the unit circle is cosine equal to 0? Pi over 2, and 3 pi over 2, right? Okay. So then, if we keep that trend, I'm going to go pi over 2, 3/2 pi, 1/2 pi, 3/2 pi, 5/2 pi, 7/2 pi. If I go backwards, I've got -pi/2, -3/2 pi. What are we saying there? How do we summarize that infinite set of values?
K is pi over 2.
Okay, it's not just k pi though, right? Because we're talking about some kind of multiples of pi halves, right? Pi over 2 plus k pi is one way we could do it. Yeah. There's another way to look at this though. We can, and that's fine. We could do. Let's take that approach for a second. So if we said the solution is x equals pi over 2 plus k pi. What if we want to get like that works, but any of these they might expect you to simplify these just a little bit possibly, which we can do. Like we could add up these fractions, for example. What would I have to do here to add these fractions up? Get common denominator, right? Multiply this one by 2 over 2, and I'd end up with let's flip these around. So I'm going to get 2k pi plus pi over 2. That looks a little weird, doesn't it? We can factor a pi out, and we get, yeah, this would be a good way to do it. 2k, if I factor a pi out, I get 2k plus 1 times pi over 2. Okay. I would argue we could have jumped right to that answer, though. What is that saying? What is 2k plus 1? If k is an integer, what is 2k plus 1? It's an integer, but it's a specific kind. Like, let's run through some examples.
Prime.
Not prime. So if k is 0, we get 3. If k is 1, if k is 0, we get 1. If k is 1, we get 3. If k is 2, we get 5. What are we doing then? Odd. Yeah, they're the odd integers, aren't they? So this is a way of specifying the odd integers, a tricky way of doing it. How would you specify even integers? 2k, right? Everybody see that? That's kind of cool, isn't it? So we knew, but we could have probably jumped right to this because we saw that our pattern here was if these are the only points on the unit circle where our solutions exist, those are at 1/2 pi, 3/2 pi, 5/2 pi, 7/2 pi. Pretty clear they're the odd multiples of pi halves, right? Pi halves, not pi, right? And so we could have said, okay, we want odd multiples of pi halves. Well, odd multiples of pi halves, really that's just saying this, isn't it? Odd multiples, odd integers times pi halves. Okay. Everybody get that? Yeah. All right. Just a little, I think it's good to go back and look at trig stuff every once in a while, because trig is, I can't overstate how important trig is with going to engineering or physics. Most of it is trig. Most of the math I did in my physics stuff is probably more trig related than anything else. Okay, so for today, what do we do? What do we do with something like that? I give you that problem right now. You can do that problem, but you got to do a little bit of upfront work in order to be able to do that problem. We want to differentiate that function. Yeah, we'd have to expand it out with it, right? We have to expand it out, and if we expand it out, we're going to get some polynomial, and then we can just differentiate term by term using our power rule. Agreed? I'm not even going to do it, but you could easily do that, right? Multiply it out, and then from there it's a piece of cake. Once you get a polynomial, the power rule is easy to apply, differentiate term by term, and we're done. Okay, there is another approach to that. There's another way of doing this. Now, and in this case, it's just a convenience, but in some cases, it's the only way to go. Like in many of the situations we're going to face even today, we don't have an option. We don't have an option. Like if we wanted to do something like, well, that one we could do, but that one we could not, right? We can't differentiate that right now because that is not one of our standard forms. We know how to differentiate x by itself, and we know how to differentiate e to the x by itself, right? What was the derivative of e to the x?
E to the
E to the x, good. But when there's a product of the two, that changes everything. We don't have a rule for that. So we need a product rule, and that's what we're going to talk about today. The product rule. I'll lead you through this. The product rule is very easy. Really, neither one of these is horribly difficult, but product rule is simpler, relatively speaking, than the quotient rule. We'll look at them both today. Here's the product rule. Let's look at it on a couple different levels. So if f of x and g of x are differentiable functions, then here's how we define the product rule, but we're going to look at an easier way of doing this. The way we'll remember it is a much more concise and efficient way of doing it. So the derivative with respect to x of the product of f of x and g of x is going to be the derivative of f of x times g of x. So if we're taking the derivative of f of x times plain old g of x, plus the derivative of g of x times f of x. Now because these things are being added, can I commute those terms? Sure, right? We know that the rules of equality for addition and multiplication they're pretty abundant, right? We can commute things, we can change the order in which we add them. We can't do that for subtraction, but we can for division, but we can for multiplication or addition. So we can flip these around safely if without any risk of making a mistake. More simply put, down here we would say if j of x is the product of f of x and g of x, then j prime is just f prime times g plus g prime times f, right? That, would you agree that's a pretty busy way of looking at it? And math gets that way. You can see in math why mathematicians take great pains to try to come up with conventions that are going to be easier to read, because it can get pretty dense, right? And so we want to, this is better than that, but I'll give you one even better than that. What if we say instead, let's just define u as some differentiable function of x, like we're making the transition here. We'll say something like u equals f of x and v equals g of x, right? And then we can do the derivative with respect to x of u times v, right? Now, this is much easier, isn't it? We end up with u v prime plus v u prime. In other words, the first times the derivative of the second plus the second times the derivative of the first. In either order. Doesn't matter, right? Very simple. So let's apply this. No big deal. So we'll go back to that first example. Rather than having to expand this whole thing out, if we use the product rule, it makes this one marginally easier. I mean, there are arguments to be made that maybe it's even easier just to expand this out first, but it's probably a little bit easier this way. So here's h. What's h prime? Okay, so we're going to do the derivative of this one first then. Okay, I'm going to do derivatives in red. So we're going to do 3 minus 4x times 5 plus 4 times 3x minus 2x. And that's it, expand it out, collect like terms, and we're done. See, I mean, really, we didn't save a whole bunch of time here, did we? And you might even say, man, why not just expand this out and do a real simple derivative? I can see the logic behind that. So far, it's unimpressive. Hasn't really helped us much, if at all. Okay, but let's try this one. So there's y. Let's do y prime. So we're going to do, and we can mix up the order this time. We've got x, so the first times the derivative of the second. What's the derivative of the second? E to the x plus
1.
e to the x times 1. And we don't really need to write the 1, but I'm going to put it there for our notes just so we see that it's a derivative. That's our answer. Yeah. Piece of cake. Okay, so we'll get some more practice with that, but let's move on to the quotient rule. Okay. Derivative, the product rule is pretty easy to apply. Quotient rule, there's a little more to this one. Quotient rule, there is an order that's a prescribed order you have to follow because we're subtracting and not adding, right? So the derivative with respect to x of the quotient of f of x divided by g of x equals the derivative of f of x times g of x minus the derivative of g of x times f of x over g of x squared. This time you can't mix it up because you can't commute subtraction, get an opposite answer, right? An easier way to think about that is using our u's and v's. Always put the u on top and the v on the bottom. That's just kind of how we do this, right? So you go in alphabetical order. So the derivative with respect to x of the quotient of u divided by v is v u prime minus u v prime over v squared. So there's kind of a little mnemonic device that you might sometimes hear calculus students say. Low d high minus high d low. Right? So we're doing low, meaning the low function, the denominator, times the derivative of the high function, the numerator. Low d high minus high d low. Okay, divided by, it's always divided by the bottom squared. Okay. The way I remembered it, back in the day, I don't know, I missed that one somehow. I just remembered it, I would always think of it as like v du dx minus, so it sounds like video. That's how I remember it. It sounds like video. The first part is v du, it's like video, minus, and then you can't, from there you can't miss. Right? However you want to do it. Maybe you're just smart enough that you don't need to have a mnemonic device like I did, and you can just remember it. Let's try it. How about this one? So what's our u?
X,
X,
5x
five.
minus 2.
5x minus 2 be
X
X
squared
squared
plus 1.
plus 1. Okay, good. So let's go. So we got y prime equals what?
X
X
squared
squared
plus
Good.
1
Low, good. We got low
times
d
5.
high minus
5x minus 2.
good. Okay, all divided by
X squared plus 1.
there you go. Okay. So we can, let's go ahead and actually finish this one. We'll simplify this. So what do we end up with then? If we do the math, we distribute the 5x squared plus 5. Now, you guys can do this for me. Distribute the minus 2x to this.
Minus 10x squared plus
Plus.
4.
You buy that? Okay. All over x squared plus 1 squared. And finally, we get, what, negative 5x squared plus 4x plus 5 all over x squared plus 1 squared. Okay, so can I go any farther simplifying this?
Yes.
What could I do?
Okay. Factor.
I mean, potentially I could factor the top. I'm not gonna be able to, What about the bottom? Would I want to expand it out? That's the question. Okay, the answer, and there's a real tendency to want to do that, especially among calculus students, because you're overachievers and you're always wanting to do more work even when you don't need to. And you don't need to. We don't want to. We want to keep things factored if we can. And how come? For reasons that will become clear later. Because what we're going to be, but I'll give you just a little bit of a hint here looking ahead. You know, when we start actually doing stuff with derivatives, we start looking at some real important applications of derivatives. Most of the time, what are we trying to do? Well, we're trying to find the zeros at the top and the zeros at the bottom. How do we find zeros? Factor stuff, right? So we don't want to ruin the work that we've already got done there by expanding it out. We want to keep things in a nice, compact factored form whenever we can. Okay? So we just leave it like that. Make sense? And this is a derivative like any other derivative. If we wanted to, let's just say arbitrarily, we wanted to find the tangent to this curve at x equals 3, what would we do?
Put 3
3
into derivative.
Okay, put 3 into the derivative to find the slope, right? And that could be the slope of the tangent line. And I could put 3 into the function to find the y-coordinate that goes with 3. So that'd give me the point of tangency then, and the slope of the tangent line, and then we just go back to algebra 1 and point slope, right? Okay? Okay, let's try another one. How about this one? Let's try one more together, and then I want to look at some other pitfalls.
So x squared plus 1.
Okay, so we got low
2
d high minus
2 to the x.
high 2x d low, good, divided by x squared. There you go. And we could do a few things there. What could we do? Well, we actually could factor, you know, while we're at it, we could factor some stuff out of the top. So let's just get a little practice at that. What could we factor out at the top here?
Let's do this.
2e to the x, yeah. We could take 2e to the x out of the top, which would leave us with x squared plus 1 minus 4x. Everybody agree?
2x.
Minus 2x, yep. Agreed? And what is the top there? Well, what is that?
Plus 1
Yeah, it's just x minus 1 squared, isn't it? Right? So we could even write this as, like, right now, we wouldn't be as concerned about it, but later in the year, when we're doing stuff with this, we're going to want to try to find the zeros of this guy, and so we would have factored that into x minus 1 squared. And that would be a good answer. You want to actually do some analysis with that derivative. Okay? Okay, so let's look at some examples here. So now, there are multiple ways to do some problems, but calculus is at least half doing things the best way. And that's, I mean that, because we get further into it, there's oftentimes there are many paths to get to the same answer in calculus, but there's one that's really good and there's one that's just atrocious that you absolutely do not want to take. The further you go in math, the more important it is to plan out where you're going with some insight. You don't want to, you want to be very efficient about this. So we could use the quotient rule here, right? Because I have a quotient, but I don't want it. Can I do this a much easier way?
You could do it
Yeah, right? We'll just rewrite this. And you don't even have to really rewrite it. I mean, at least in your mind, you're recognizing that I could rewrite this as y equals 5/8 times x to the 4th. You don't explicitly have to even rewrite it. Just when you take the derivative, you think of it that way. That's a lot easier than having to go through that whole process of the quotient rule, isn't it? And the quotient rule is unnecessary because low d high minus high d low, what's the derivative of the bottom? What's the derivative of a constant?
it.
0, yeah, right? So what good? I mean, just a lot of work for nothing. When we differentiate that, what are we going to get? We've got our constant out front. So 5/8, what's the derivative of
4x.
times 4x cubed? And then we just would simplify. What do we get for our answer when we simplify? So 10, what was that going to be? 5 halves. 5 halves x cubed. Okay. The important moral of the story being, we never apply quotient rule if there's a constant on the bottom. Never use quotient rule if there's a constant on the bottom. Totally unnecessary. Would it work? Yeah. On a paper and pencil test, would I give you full credit? Probably not. I'd probably take a little bit off, because it's not the best way to do it. Same thing here, right? What would we do here?
Take
Power
out
of
of
1/6.
1/6.
And we could split this into two parts, right? And just differentiate term by term.
Yeah.
Make this much easier. Right, so we don't even have to probably write this down, but in our head, we're thinking y equals 1/6 x squared plus 1/2 x.
Yeah.
And then we differentiate and we get y prime equals, what's that gonna give us?
6 to x.
So yeah, 1/3 x plus x plus 1/2, and that's already simplified. Make sense? Okay. So sometimes I call this pre-writing. Before you even do the problem, you want to rewrite the function in a way that's going to make it easier to differentiate. And that's, like I say, the further you go with this stuff, the more critical that becomes. So what about this one? Looks an awful lot like the quotient, doesn't it? Do I have to use the quotient rule here?
You could factor out
Factor
the
out
x.
an x.
I mean, I could factor out an x, but I don't need to. I can just split this up into two terms, right? Everybody see that? If I split this into two terms, let's see what happens. So I'm gonna get, I'm gonna get negative 9x over 7x. What's that? Negative 9/7, yeah, is the first term. What about the second term? I'm going to get positive 6x squared over 7x.
6x.
Easy, right? When I differentiate then, I'm going to get 0 plus 6/7. 6/7. Okay? Right, so what's the moral of the story there? If you can split the fractions up, and when does that happen? What would have made this much harder? Like, what if I had, this makes the problem a lot tougher if I've got something like 7x minus 1 on the bottom. Now I'm stuck. Right? Now I can't just split that up and divide the x's vertically, right? But if I've got a monomial on the bottom, a lot of times I can split this up into separate terms and make the derivative process a lot easier. So what about that one? Now I do have an x on the bottom. Darn it, do I need quotient rule?
No.
What can I do there? Negative exponent, there we go. So we'll just rewrite that as y equals 9/5. I can just put the 9x to the -2 on the top, right? And now I can use a simple, that power rule is so easy to use. So we get y prime equals -18/5 x to the what? -3, good. So then if I simplify, if I rewrite it, with maybe a positive exponent, -18/5x cubed. Okay? All right. I'd say just get some practice on this. There may be some questions might pop up, but I almost feel like it's better if you do a few of these first and then we'll look at questions. This first assignment is a pretty short one. We'll go, the next step is, so can you imagine, just to give you a little insight here where we're headed. We know how to do the derivatives of sine and cosine, but I haven't given you like tangent or cotangent or any of those yet, right? How do you think we might find the derivative of tangent x now? But how do you think we might come up with that? Might derive the derivative of tangent x? If I know y equals tangent x and I want to calculate y prime. Sine over cosine, right? Now I can do that, can't I? If I write tangent as sine x over cosine x, I know the derivative of sine, I know the derivative of cosine, I can use the quotient rule and do this as a quotient, right? And come up with some answer. So that's where we're going next time.